I'm Tran from Ford Street High School, Year 10 Electronics. Today I'll be showing you how to build a digital clock and how it works. We will be assembling a clock kit which features a 4-digit 7-segment display. To begin, I will be conducting a stock take of the components being used and where to solder them.
5 4.7 kilo ohm resistors in R1 to R5, a 470 ohm network resistor in RP1, a 10 microfarad electrolytic capacitor in C1, 2 picofarad ceramic capacitors in C2 and C3, a 100 microfarad electrolytic capacitor in C4, a 104 ceramic capacitor in C5, 2 1N4007 diodes in D1 and D2, a 12 MHz crystal oscillator in Y1, 2 push button switches in S1 and S2, a 8550 transistor in Q1, a 564 AAS1 display in SMG, a TMB12A03 buzzer, a DIP20 IC socket, and a AT89C2051 IC, which both belong in U1, a power terminal in J1, and finally the PCB.
It is important to note I'm wearing eye protection and working on a relatively heat-proof surface, that being a writing pad. I begin constructing the circuit by soldering the resistors, as they are the shortest components in terms of height. I then solder the diodes and ceramic capacitors. Then goes the oscillator and network resistor, followed by switches and electrolytic capacitors. I'm using foam to prop up the components from behind to ensure that they are flush and square with the PCB and aesthetics. Off go the component legs and back to work with soldering the IC socket, buzzer and terminal. While waiting for the time lapse to catch up, note that you need to be soldering in a well ventilated area. As good as they are, the solder fumes are not good for your health. Finally, the 4-digit display is soldered to the PCB. Job well done, Peter. So I hope you enjoyed that little time lapse of how we built our circuit. I'll show you now the functioning circuit. You will notice I've attached a USB cable to our power junction to provide power for the circuit. You could also attach this to a DC wall adapter or even a battery. So, how do you use the clock functions? Well, luckily the instructions were in Chinese, which means we can't read them. So after a bunch of trial and error, I figured how to use it. When attached to power, the display will show 12 o'clock. Please note this clock is in a 24-hour time format. To adjust the time, press switch 2, then switch 1, and the first digit will begin to flash. That is the first digit of the hour. Use S2 to change the first digit. When that is correct, press switch 1 again to change the second hour digit, using S2 to adjust the time. Follow this process to change the minutes as well. When you finish doing the last digit, pressing S1 will change it so you're viewing the minutes and seconds. And press S1 again to return to the main view. And that is the basic functions of the clock. The 4-bit digital display. The 4-digit 7-segment display has many applications. For example, to keep score in a sports game, but today we'll be using it to display time. There are 12 input pins which control the display. Each of the 7 segments is labelled with a letter from A to G, corresponding to an input pin in the display. Also, Each of the 4 digits has an input pin associated with it. The final pin remaining controls the decimal point labelled DP. The display works by powering the relevant pins to produce a number. For example, to create a 2 on the second digit, pins D2, A, B, D, E and G will need to be powered. Following that logic, the display can only show 1 digit at a time. Well, that would be a terrible display. Well, luckily, the display cleverly employs the persistence of vision phenomenon to trick our wonderful minds to see multiple digits. The display uses a 5 millisecond delay between each displayed digit to trick our eyes to see all 4 at the same time. The crystal oscillator is one of the many types of oscillators, which include the Hartley, Colpitts, RC, and Weinberg oscillators. An oscillator circuit produces a continuous clock signal in the form of a square wave to coordinate the function of a microprocessor. A square wave alternates between a high and low frequency. The crystal oscillator is able to sustain a very high level of oscillator stability, crucial to a stable and constant circuit. Quartz is usually the crystal of choice for its high mechanical strength and the piezoelectric effect, which occurs when a voltage source is applied, resulting in the crystal changing shape. The piezoelectric effect means that the electrical charge becomes a mechanical force. As such, the crystal oscillator is classified as a transducer because they convert energy from one kind into another, that is, electrical into mechanical. The mechanical force is in the form of vibrations or oscillations at a specific frequency, depending on the size and thickness of the quartz crystal. This is a diagram of a typical crystal oscillator. We can see the 2 microfarad capacitors, which will be providing the voltage source. The output of the oscillator moves directly into the microprocessor. In our digital clock circuit, the 12 MHz signal travels to the AT89C2051 chip. Now that was a perfect segue into our microprocessor, the AT89C2051 chip. It is a low voltage, high performance 8-bit microprocessor featuring a full 2 kilobytes of flash memory designed by Atmel. It is a 20 dual inline pin through-hole integrated circuit chip and takes clock timings from a 12 MHz oscillator, like the one found in our circuit. Each of the 20 pins interacts with a specific area of the circuit. Pin 1 is the reset input. Pins 2 and 3 connect to digit 1 and 2 respectively on the display. Pins 4 and 5 are the XTAL pins, which connect to the crystal oscillator, so the microprocessor has a clock to run with. Pin 6 connects to digit 3, and pin 7 to digit 4. Pin 8 and pin 9 connect to 2 push-button switches, which allow the user to adjust the time and clock functions. Pin 10 is the ground pin. Pin 11 connects to the buzzer, which provides a sound output. Pins 12 to 19 are output buffers which power the display segments via the network resistor. The segments powered by pins 12 to 9 respectively are the decimal place, G, C, D, E, B, F, and A. Finally, pin 20 connects to the power supply. And there we have it. We've finished our digital clock display and we know how it works, from the 4-digit 7-segment display, how the crystal oscillator and the microprocessor worked in our circuit too. I hope you enjoyed this video. Please be sure to check out our other videos and make sure to leave a comment, like and subscription.